So now we have to look at particle filters under modern topics in stochastic processes as we gradually bring this playlist to a close. After this, I have one more, and we'll bring the stochastic processes playlist to an end. So particle filters, or what you can refer to as sequential Monte Carlo, are a class of algorithms used for estimating the state of a system that evolves over time. They're especially useful when the system is non-linear and the noise is non-Gaussian. So that means the noise does not follow normal distribution, if you like. So unlike Kalman filters, particle filters approximate probability distribution using samples, or what you can call particles, just like what we saw in the last video about Monte Carlo method, where you talk about samples. The more samples you have, the better your estimation would be, whatever, as you use Monte Carlo simulation. So the problem set up in the case of particle filters is like this. We consider a general state space model. So you have a state transition x of t, which follows the probability of x of t given x of t minus 1. And then you have the observation model y of t, which follows probability of y of t given x of t. And the goal is to get the probability of x of t given that y1, given y1 is t. So this is the posterior distribution of the state given observations. Then we move on to talk about particle approximation. We are talking about particle filter, right? So we approximate the posterior as probability of x of t given y1 at t, which follows this summation from I equals 1 to n wti delta xt minus xti, like that, where the xti's, these xti's are the particles, while wt of i's are the weights. And then we have n to be the number of particles. So n is the number of particles you're dealing with. And then we have the algorithm steps. So talking about the algorithm steps, first of all, at each step, you have number one, initialization, where you say x naught I. That's, of course, like we know the particles at time zero for, so x naught I is, just like probability of x naught. And then step two talks about the prediction. So for the prediction, you have xt of I, which follows probability x of t given x of t minus 1 at state I. And then you have an update. So for the weight, WT of I is directly proportional to P, probability of Y of t such given XT I, like that. And then you can normalize. So the normalization is WT of I of the weight now. So WT of I equals WT of I at I all over summation over J of WT of J. And then you can resample. So for the resampling, you can resample particles according to weights. So for each at each time step, you have all this initialization, prediction, update, normalize, and resampling. And then we move on to this a simple 1D tracking example. So if you model state transition, which is x of t equals x of t minus 1 plus v plus epsilon sub t, then the measurement can be taken to be y sub t equals x sub t plus eta sub t, where epsilon sub t is normally distributed with mean 0 and variance sigma squared, and eta sub t is normally distributed with mean 0 and variance sigma squared. So if you want to simulate that now, then you can have this kind of system here. You import. We are using NumPy and Matplotlib to visualize. Now, this line 4 is really important when you're dealing with random systems. So if you want to have the same result all the time, so you have to set the random seed. So 42 is a common number to set. There are other numbers you want like that. So here we take number of samples or number of particles, that's 1000. Time is 50, velocity is 1. So you can then initialize. You have particles. So following that random distribution from 0 to 1 over the n samples, the n particles. Then you have the weights now, np1s over n. Then, so this is like the weights, the weights like that. Then true sub x equals 0. So that's used like some kind of initialization. So you have two states and estimates. So you are declaring this to receive them as you update. Then you have the true motion. True x is true x plus velocity plus, you have a measure of randomness, which the epsilon sub t represents as you have it here, like that, for a simple 1D tracking, right? Then you have the measurement, like that. You have the prediction for the particles. You have the update weights. You have the normalization. You have the estimate, and of course, you have the resampling. So, so you have that, and then of course I've run that second one. Now we want to have a look at it. So now if I run this now, we want to see the particle filter tracking. So the true state is in blue and the estimate is in orange. So it's like we are trying to make the orange fit. We are trying to track the reality with the estimate. So I tell we sum up the particles multiplied by the weights, right? So particle multiplied by weight, and we sum it all up like that. And that's exactly why we have this now. So you have the true state and the estimate. Then we go ahead to talk about the importance of sampling. So weights are computed as WT of I at state I, directly proportional to probability x of t at I, given y1 at t, all over q of xt at I. So in practice, we often use WT of I, which is directly proportional to probability y of t given x of t at I. So, and then you have a degeneracy problem. After several iterations, many weights become nearly zero, right? And only a few particles dominate. And then the solution is resampling, right? And then that takes us to the concept of effective sample size, ESS. So ESS is 1 over summation from I equals 1 to n of W1 squared. So if ESS is small, then resampling would be needed. So if small ESS means we need resampling. So in this case now, so imagine you define a function called effective sample size for the weights, and then you return 1.0 divided by sum of the square of the weights. So, and then for the weights now you can then have like 0 0.1, 0 0.2, 0 0.3, 0 0.4 like that. And then you can verify if weights are normalized. So you have sum of weights equals sum W, sum of the W you have here now. So then you print sum of weights, and you know you want to go through all that processes. So this helps you to know if the weight is normalized and things like that. Else, weights are not normalized. So this is a check to see if there's normalization. And then, so if you, by the time you run all that, right, you see sum of weight is 1 and weight, so that tells you weight is normalized. So, and then effective sample size is 3.33. And with that, we go on and then we talk about systematic resampling, which we see here. You define a function, systematic resample with the weight, and n is length of the weight, and you have the positions, you have the indices, np zeros, and all that, and you have the cumulative sum, and you run all that. So, and so we keep that ahead. Should we even print the indices? So you return indices. Okay, maybe something I can do here is to, okay, we need it for the next state for sure. I think we need it for this next stage. So now we have set this systematic resampling ahead of the non-linear example we want to look at here. So for the state transition, you have x of t equals 0 0.5 x of t minus 1 plus 25 x of t minus 1 all over 1 plus x of t minus 1 squared plus 8 cos 1.2t plus the random part epsilon sub t var epsilon, that is. Measurement then is yt equals xt squared over 20 plus eta sub t. So then you can have so you define the transition matrix for x of t, and then you return 0 0.5. So this is this whole thing defined right here, and you have the measurement model as x squared so over 20. That's what you have here. And then for the number of particles, you have 1000, and you set everything in place, and you can run this now, and that gives you you know so of course you also want to do the figure. So, and you have this now. I suspect that, I think that it's like, okay, we set a seed for this, so it gives the same result. It doesn't keep changing. So if you don't want your result to keep changing, you want to set a random seed or so that you make sure that it is reproducible. So certain seed is for reproducibility, so you don't keep getting different results each time you run the code. In summary, we see that particle filters represent distributions using samples, and they handle nonlinear and non-Gaussian systems, and then they use prediction, weighting, and resampling. So the key idea is that a set of particles evolves and adapts to represent the posterior distribution. So, okay, this should actually be practice problems, practice problems. So we have that. So we have conceptual questions. Explain why particle filters work better than common filters for nonlinear systems. Yeah, I mean, we talked about all of that. So try to look at this question. This is 1 to 10. And this here we have some mathematical problems. Given with this, verify they are normalized and compute. So you can do like the normalization kind of thing we did the other time. I mean, that's literally what we even did. Then suppose YT is 5 and particle states are 4, 5, 6, and all that. So compute unnormalized weights, assuming this expression here. Then normalize the weights obtained in 12. Show that if one particular has weight 1 and others 0, then ESS is equal to 1. Then show that if weights are uniform, WI is 1 over n, and then ESS is n actually. So that's like, yeah, summing it all up. Then you have the coding or applied problems. Now you can modify a particle filter so that resampling occurs only when ESS is less than n over 2. So it's just about modifying the code we had before. Then you can simulate a system, just like the one we did before, and implement a particle filter for it. Increase measurement noise variance and observe how particle spread changes. Then reduce number of particles, e.g. from 1000 to 50, and observe performance degradation. Of course, I think the whole particle filter thing also follows the idea of Monte Carlo, where the more samples you have, the better results you get. So performance degrades when the number of particles reduce. So reducing particles is more like you have less samples to deal with. So you can then implement and compare multinomial sampling, systematic sampling, and you want to find out which performs better and why. So try your hands. Again, look at questions 1 to 10, conceptual questions that you can just answer, and then all the rest. So you have 11, 12, 13, 11 to 14, then you have 15 to 19, then I show 20, now 16 to 20. All right, let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel, I thank you very much for doing that. If you haven't subscribed, what exactly are you waiting for? Why not go ahead right now and subscribe? Hit the notification bell also so you can always get alerted each time a new video is released. If you also like, you can become a member of the channel. That gives you special privileges like seeing some videos first before other people, or being the only one seeing some videos exclusively as a member of the channel. You could also request for PDF copies of my notes. We can also hang out physically if you're in the same geographical location, or hang out virtually to discuss whatever interests you on my channel, be it mathematics, data analysis, data science, machine learning, scholarships, writing books, anything at all that fascinates you on this channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.